What if the unknown standard deviations are assumed to be unequal? Then we modify our process slightly, using this formula for the standard error. Also, for obtaining our t-distribution value against which to compare the test statistic, we use this value for the degrees of freedom. We now consider a case where the samples are actually dependent on one another. That is, each observation in one sample is associated with a specific observation in the other sample. For example, suppose we are tracking weight loss. We want to determine whether the average weight loss is statistically significant, so we need to match each individual's current weight with their previous weight for the study to have any validity. We again use the student's t-distribution, and call this type of hypothesis test a paired t-test. We explain the process using an example. We will determine whether the drop in cholesterol level within a small sample of patients is statistically significant. Since the old and new cholesterol levels are paired, we can simply examine the individual differences in cholesterol level for each patient, which is denoted by the variable d. Then we have a sample mean d bar, that is 10, and a sample standard deviation of 8. That is, even though we have two samples, the fact that they are paired allows us to work with a single variable d. We choose alpha equals 0.01 for this test. Our research hypothesis is that the medication does significantly reduce cholesterol level, so the alternative hypothesis is H1 d is greater than 0, and the corresponding null hypothesis is d less than or equal to 0. We then compute the standard error. Note the similarity between this formula for the standard error and a standard error of a mean for the one sample case. This is because we are treating a difference of the two paired samples as a single sample. Then we have our test statistic that is computed in the usual way: sample value minus hypothesis value divided by the standard error. We then compare this to t alpha n minus 1. Note that again we are acting as if we are working with one sample instead of two, as we are using only n minus 1 degrees of freedom, rather than n plus n minus 2. This is because the pairing takes away additional degrees of freedom. Finally, we compare our test statistic to our threshold value, t alpha n minus 1. Because the test statistic is greater, but our null hypothesis is d less than or equal to 0, we reject H0 and conclude that the difference of means is statistically significant. That is, the medication is effective. Finally, we will learn how to test for a difference in proportions. We will continue to assume, as we have been for proportions, that the sample sizes are large enough to assume that the populations approximately follow normal distributions, which closely resemble the binomial distributions that they actually follow. We refer to the population proportions by P1 and P2, and use P1 hat and P2 hat to refer to the sample proportions. There are two cases to consider. If our null hypothesis is that P1 minus P2 is being compared to 0, for example P1 equals P2, then we pool the samples together to obtain an estimate of a proportion of the combined populations. Then we use this formula to obtain the standard error of a combined proportion, which is similar to the standard error of a proportion for the one sample case. But if a difference of proportions is being compared to some other value in our null hypothesis, for example assuming that there's a specific gap d0 between the proportions, then we do not pool the samples and instead use this formula for the standard error. In both cases, we use the same test statistic, which has the same form as always: sample value minus hypothesis value, which may be 0, divided by whichever standard error is being used. We have seen several hypothesis tests for different purposes: testing a mean, proportion, difference of means, and difference of proportions. We have seen one-tailed and two-tailed tests with known or unknown population variance, large or small samples, and more situations. We have also seen that the actual test can be performed in different ways. We can check if a sample value falls within a confidence interval, or we can compute a test statistic to some threshold value based on a standard normal distribution or t-distribution, or compare a p-value to the level of significance. To help keep track of the many processes that are used in these varying situations, it is helpful to keep in mind what they have in common. The test statistic, as we have seen, is always computed in a consistent way. If the variances are unknown, we should use the t-distribution instead of a normal distribution, though it does not make much difference if the sample sizes are large. Of course, a sample standard deviation should be used in this case for computing the standard error. It's also worth noting that the p-value is always a probability that the appropriate standard random variable compares to the test statistic in some way. The specifics are determined by the type of test, one-tail or two-tail, that is being performed, and whether the variances are known or unknown. To conclude, we note that the main difference among the many hypothesis tests we have seen is in the formula for the standard error, so they are summarized in this table that continues on to the next slide. It should be noted that when a scenario includes an assumption that the sample sizes are large, the formula still applies if the populations are normally distributed, even if the sample size is not actually large. And here's the remainder of the standard error summary.